for smart manufacturing landscape, which is a very interesting upcoming topic, because the working group 23, who is doing that, has started only 2 or 3 years ago. It is a new working group in IEC DC65. It's not the only area where smart manufacturing standards are done. It's ISO DC 184 as well, industrial and automation and integration. So you see there, and there are joint working groups as well. As it's a really upcoming huge landscape here. I must do some acknowledgement. I show some slides from ongoing work, so that are not, most of these standards are not finished or published at the moment. It's work from the working group where I'm participating since the last several years, and therefore beware, it's not the standard, but anyway, in research, it shows the directions people are going, and I think that is very important in such a conference here. Yeah, not just to read a standard. Yeah. The contributions were co-funded ours from the European Commission in several Excel projects, which are large European industry-oriented projects, and we are a research partner here in most of them. And I am personally involved in the standardization work packages, which is a mandatory part of this type of projects. What is now smart manufacturing? There's an ISO definition in NTR. Yeah. It is manufacturing that improves its performance aspects with integrated and intelligent use of processes and resources in cyber, physical, and human spheres. That means it's very integrative, and it delivers products and services, yeah, and collaborates, that's very important, with other domains, complete supply chains, etc. Also it is more than just a factory and more than just one production process. It's agile, it has to be safe, efficient, and optimizable. Also that are additional factors to the conventional manufacturing here. And other domains like engineering, logistics, marketing, procurement, sales, the order sequence, and all the things control here somehow additionally the production process and align it. And there is a standard in ISO as well, safety of machinery, guidance to machinery manufacturer, consideration of IT-related security. That means security, of course, is because it's much more connectivity than a closed manufacturing process. Therefore, cybersecurity is much more important. And of course, safety remains as important as it was, with additional factors that it, of course, includes many more interfaces and connectivity. This is a general industrial safety and cybersecurity landscape. Yeah, I have in the left corner written the standards which are now on smart manufacturing IC. It's 63283. Most of them are reports. That means it's an initial state. It's not having mandatory requirements. There are more recommendations in these types. We have terms definitions. We have used a lot of interesting use cases. That was the basis that industry should provide these use cases. Then we have challenges for cybersecurity, the inclusion of new technology, as it was mentioned before, AI particularly, but also 5G and all the other new technologies have to be integrated. This part is not developing new technologies. This part is just considering upcoming technologies, how they impact the manufacturing process, and what, let's say, challenges have to be additionally tackled here. And there's a part 5 on market innovation trends. You see this landscape here. I must see. Okay, they cannot make the pointer here so easily. Okay, with the basic safety standard, with the smart manufacturing standards. Blue circles here, and we have the digital twin and roadmap asset and administration shell standards as well. And on the left is an automotive part, which will be handled by my colleague Christoph Schmidtner, with IEC 62443 as a basic functional security, basic security standard, industrial security standard, and a basic safety standard. And in between, a set of many domain-specific derived standards from these basic standards. This 62443 standard is becoming now a horizontal standard. That means it should become a basic security, let's say, specification in the future, like 658 for safety. As this is an ongoing work here. What is now different and most important for the production systems, it's all is digitalized. Yeah? From design to decommissioning, you have a digital representation, you have digital twins, and you are planning on the digital part before you are even simulating and testing it first in the digital representation before it is installed. And of course, it is not only when you install it, it's also a live issue. That means it is optimized throughout the process and may change in an agile manner if you change your products, etc., and adapt them. The digitalization, of course, needs a digital twin, which is a separate ecosystem. You see here how many groups are working on digital twin issues in ISO, IEC, in the enterprise systems. That's 650 and 650E, that's the enterprise system IC, that's the advisory group GTC1 with IoT, with AI and several others, and joint working groups, and of course outside of this, but somehow cooperating and even influencing these international standards are a lot of industrial associations which contribute as well. What is the difference in the automation process? The automation pyramid is this well-known pyramid from the signals to the enterprise system. And in smart manufacturing, you have a much more complex, let's say, picture here. You have components, machine, you have factory, but you include order, you include supply chains, and you include outside your own side as well, many other organizations which contribute somehow to your production planning and adaptation, commissioning, etc. And of course, the product. You have the, let's say, digital type, and you have the instantiation in the end. This is a network which is called a value streams network, and not only a value stream, but a value network. That makes this much more complex, and you see all these interfaces here in between. Okay, what means smart? Smart means somehow intelligent. In this reports, people have thought about these intelligence levels as well. So everything is somehow organized in levels, and you have different, let's say, topics here: perception, you have artificial intelligence, data information, data services, you have cooperation and interaction between the different elements, you have adaptive optimization, interconnection, intercommunication, and monitoring and control, of course. And you have several levels here, from simple and none, that's a conventional way here, yeah, up to manual, scheduled, and so on, until predictive sensoring, and that is even funny, intelligent like human. I try to avoid that things like that become at least part of a report, but anyway, people wanted to go beyond self-learning as well. But anyway, you see this increasing levels of intelligence and automation here is somehow critical here, and this provides additional new challenges. You have these properties and assessments. Here are some examples. That, of course, there's more than 100 pages in the usage cases of the standard, 150 or so, and you will see many examples for requirements here, sensoring, data acquisition requirements, information processing requirements, and in artificial you have machine learning, the capability to acquire knowledge, model-based inference, decision-making, and of course accumulation. That means memory of knowledge base. That means these systems accumulate information and knowledge from the ongoing processes over time to allow, in the end, optimization. Here we have some requirements on different levels. They have made a lot of nice tables here. Perception goes from none to have no data. You have human perception, you have semi-automation. That means some preliminary information. You have for processing. You have automation perception, which collected it and processes, so it's automated. And you are predictive on level 4. The standards of predictive maintenance, predictive optimization, etc., are becoming more and more important here. And that's, of course, somehow in an automated manner beyond conventional manufacturing and production. The same levels you have in the eye, and you can consider different properties here for these requirements. We have for cyber security, for the classic industrial automation control systems, the 62443 series. Yeah, we have the general standards, and the red ones are just upcoming and under development at the moment. They are the profiles. They have seen that IEC 6244 is much more triggered by the conventional process industry in the past. And now they have said, okay, they want to make it at the task force roadmap here. Yeah, they want to make it a horizontal standard. And that was decided just recently. The result of this task force, I was member of Wesel and strongly supported that to make it a horizontal standard or basic security standard for the industrial security. Then you have you need, of course, if you adapt it to different domains, to make profiles, and you have two standards here: rules for profiles and the profiles themselves on the component product level. And then, of course, you need at some level security evaluation methodology, also to be able to audit and to certify it. And that's done for the service providers. That's here. 2461, and done for the components. And here it meets somehow, which was also, let's say, proposed already in the roadmap, beginning of the roadmap sessions, that you have to look, of course, and common criteria and elements like that too. So there is some alignment between these different standards in ISO and IEC. That's in classical. A manufacturer has typical security level zones and conduits. I will not repeat zones, security levels and so on, and foundational requirement. Maybe they are well known. If not, I will have it in the slides which are distributed afterwards. You have here this example from Inge Rolle, which was presented at one of these meetings. We have an oil platform. You have the zone A, where you need a low seal, have a low safety level, yeah, in the zone A, and need a high security level because you need some standard equipment outside with untrained users. And of course, it's an open system here. In the conduit in the bottom, yeah, that is almost autonomous and automated to be safe. And here, of course, you have a high seal and low security level. This zone conduit concept is important in the area of this industrial security. And what is now different in smart manufacturing? You have this value stream between enterprises. You see this picture here, yeah. In the middle is this, let's say, factory, so to say, or production site, yeah, with processes, resources, products, services. But you have a connection to other domains like supply in the upstream enterprise and downstream, the delivery until decommissioning and so on. And we have a complete set now here, which integrates in the enterprise value chain more than just one enterprise. Now, what is now particular for cybersecurity? What's different? You have more multiple stakeholders or asset owners, yeah, production, equipment, process, data analytics, services, and you have to balance these different stakeholders inside and outside. Yeah, then continuous change in the reconfiguration. That means it's optimization, the adaptation to changes in products, and even in changes in machinery and components, which have to be, let's say, adapted on the process. Then digitalization, of course, digital twin, etc., distinctive planning, tools for simulation engineering, product engineering, and process engineering. Architecture, this automation pyramid I've shown already, and there are a lot of standards here mentioned in this list from ISO, IEC, and so on, down to and up to industrial IoT, etc. That means you need to adjust your security architecture just additional to this zone conduit process. You have wireless networking, 5G and so on as new technologies. You have much more communication and different technologies used here. And of course, you have smart means intelligent, partial autonomy and decision taking. Here comes in artificial intelligence, machine learning, let's say, maybe not on the spot, but in the tooling and preparation and prediction mechanisms. And all this brings new paradigms in it, which are handled, for instance, by this TR 5469, Functional Safety of AI Systems, which is a cooperative work between the basic functional safety group 65008 and the GTC1 artificial intelligence trustworthiness group. Yeah? And of course, for security, you have additionally industrial specification group on securing AI. So I will have a short discussion about that later on. And of course, you have to include systems engineering because you handle here, of course, systems of systems. As an issue that was criticized in 608, that it's not taking up the systems engineering concepts. In some derived standards, like for cyber warfare and industrial standards for defense industries, that have taken up the system engineering aspects as well. So that is, let's say, some process, and it's done in smart manufacturing too. So they have a particular long chapter on how the processes which are defined in the system engineering standards are adapted and used in context of smart manufacturing. And there have been several recommendations for improvement of this industrial security standard. Yeah, that means specific terms and definitions have to be aligned with the extend this virtual zones context except to this more networked concept to include the digital twin concept. You have to adjust risk assessment security levels because it could happen that parts have other, that even an existing manufacturing system can switch between different security levels depending on the actual context of production and products. So even if you adapt the process, you might even have different security levels to look at, stronger or weaker as before. Then you have to align the security life cycle to the smart manufacturing systems. I've shown this picture before, where much more is in this network included. And they have to consider the product and data as an integral part. So it's very data-driven, yeah, and even feedback data-driven. So that is an additional feature here. And of course, auditing and logging has to be extended because of the more complex architecture of such systems. You have this protection goals as classical ones, and they have that extended that to different viewpoints. So in these documents of these reports, yeah, you have a use case view, that's the most important one. You have a technology view, yeah, which discusses the threats to new technologies. It's as an example, artificial intelligence is one example, and they have a life cycle view because of this additional life cycle dependencies of this more extended manufacturing systems. And there are a list of 16 use cases in this DTR, and one has been selected, the modularization of production system. I've selected one of the use case examples which I like for certain reasons here. You see this production process, we have the resources, you have the interfaces at the product design on the left. You have production system engineering tools that are tools where you plan the production and configure your system. Yeah, you have a system integration engineer where these digital entities or assets are integrated and implemented in reality. You have the production system design engineer and the integrator here. And then on the right of the production resource integration, that means you build together according to your process and product, different machines in an adaptable production system, which can be even on the fly doing the optimization, doing changes in the products and adaptations. Yeah? So this picture is used generically in this standard. And for instance, we have the steps 1 and 2. One means they've made now different considerations on the threats and vulnerabilities. Field device adds itself to the production system, one key feature of smart production, yeah, and may access information not intended for its device, or a new field device let's say, impersonates another field device that simulates it and offers a functionality it is not provided for, yeah, and to get access to confidential information, for instance, or to, let's say, interfere with existing process. This example shows the threats which I just mentioned, the issues which are handled confidentially in these two cases, yeah, and the challenges are numbered. Use case 5, the long lists of different challenges. Control of field devices, that means you need to set according to the intended task and provisions different for these elements and assets, depending on its place or its role in the, let's say, configured process. And of course, you need an authentication of devices and sensors, etc. These are the challenges. And these are particularly the first one, of course, smart manufacturing specific, because normally a field device cannot add itself, but it is the case in smart manufacturing. Then it goes on. You have other issues in 3 and 4. You see these red circles here. A compromised new field device disturbs the production process, or an attacker exploits some states. If you change a configuration or a production process, yeah, then of course are always some intermediate states which, at least for some short time, have not a defined security level, and that means that could be exploited. And for this, they have some rules as well. I will not show all these tables, but just to show the ideas behind it. And the last steps are an attacker takes benefit of the protection gap of some individual device into a transition. Yeah? For instance, the zone protection will fail while a device is relocated. That's 5 here. And an attacker defines a new configuration state that could happen as well. That means in all of these 3 major phases here, resources and interfaces, production system engineering and integration, and production itself, there can be additional challenges for security. And of course, of safety, I focused here particularly on security issues. There's a sum. Yeah.
Having 3 minutes left. Please prepare for landing.
That's impossible. Okay, you have these cybersecurity challenges: identification, authentication control, use control, data and system integrity, data confidentiality, timely response to events, restricted data flow, particularly that's important for reconfiguration, and resource availability. So this and all of this, they have tables like this one, where they have let's say, operational measures or secure countermeasures, security ones. And these are listed here for all of these different challenges. Use control is a self-descripted information of system that is really typical just for smart manufacturing because of this ability to integrate on the fly, so to say. Then we have this optimization, design engineering for artificial intelligence. They have defined in this part 4 different roles for safety, trustworthiness, and the engineers involved here. Yeah, you have a data scientist on the left that develops and trains a prediction model. The software developer develops this execution module of this abstract prediction model, which is outside the production process, and integrates it in the tool landscape. This is executed during the processes in the next step. And of course, it is optimized afterwards because that they are taken up during the process of data, production data. Yeah. And of course, the challenges are AI and ML process trust. That means robustness, safety, security. This trustworthiness is a key definition from the systems engineering standards in ISO, and it includes more than safety and security, a lot of other characteristics as shown on this page here. And this you can find, of course, on the websites of the Square, also System Software Engineering. I have a very short overview on how functional safety and I is handled. There's a DTR between ISO and IC, which I mentioned already before, which is under development. At the moment, there are the steps where I say, okay, we have different technology classes, yeah, how this AI element is developed, making existing functional safety methods not fully developed, or with developed using methods which cannot be analyzed in the conventional manner as prescribed in the functional safety standards. Then you have this application use cases as where is this element positioned in your system. Yeah? It is safety relevant and automated decision making it's doing. Then it's A2. It's safety relevant, but has no automated decision making, for instance, uncritical diagnostics. So if diagnosis does not impact, let's say, the processes in the system afterwards online, then it's used to develop some safety relevant DB systems as offline support tools. That's B. And in C, it's a little bit outside. This has some potential impact on safety. For instance, it can increase the demand rate on the system or can make time delays, yeah, but not direct interfere, or it is not part of a safety function. And this picture, which is the current status, I'm not sure, there are hot discussions still on this. It is ongoing process. Sometimes I'm contributing to it. Yeah? You see in the highest class 3, most of this level A and B are not recommended. And in the other classes, it's somehow possible to use it, or let's say with some additional measures. That's a yellow part here. Might be allowed to use it in critical applications. So this, let's say, characterization is established. At the moment, we have not. It is not developed the rules for that. So if there are not more,
we're running out of time. I think
yes, that's
going to come to the
at the end. You see, in ETSI, you have a cybersecurity report for artificial intelligence that includes data acquisition and data curation and model design on the one hand, and of course, after implementation by building, training, and testing, yeah, it's deployed, and of course, there's results and lead to updates. And here are specific security challenges as well and safety challenges. You have made a list for the design challenges and particular on unintentional factors like bias, yeah, explainability, even ethics, as even as ISO standard, it is ISO working group trustworthiness on ethics. Yeah, that means mainly privacy and the role of humans in a process. Yeah, and of course, attack awareness and misuse should be increased. You see all these different features are here, and that are very nicely here. Let's say in this report. Okay, that's it at the moment.